Last time we looked at the binary search tree. It's a data structure that lets us add, remove, and traverse in reasonably fast time, and it lets us search very conveniently. However, what if it had a problem? What if we add to our binary search tree a data set that's already in order? That might sound like it's a blessing, like we're adding something that's already sorted. We've done the work, but look what happens to our tree. It just gets taller and taller and taller. And what do I mean by taller? Well, I mean that every node just has one child. So we have to traverse through all those nodes when we want to add. That is the key to the time complexity of our tree. Our methods are fast because they don't iterate over everything in our data set, but they iterate over the height of the tree where we're adding. Let's look at this search method for an example. Our search never goes up and then back to another child. It only goes down the chain of children, right? So the maximum amount of steps it can take is the maximum length of a chain of children it might have to follow. Same thing happens with add. So we can say that the time complexity of our tree methods is bounded by the number of children, the maximal number of children a node can have, which is what we'll call the height of our tree. So how do we make sure the height of our tree stays low? Well, let's think about a small tree, just of size 3, and let's try to apply those ideas recursively. In a tree of height 2, we have a child, a root, and another child. But we can also get this tree to be of height 3 if we have a root and then 2 children on one side. What does that tell us? Well, it tells us that a tree whose nodes are filled, a node which has both children, is going to be better for our time complexity than a node with a chain of children. And if we go through and we take this logic through a whole tree, we can say it's a complete binary tree where all of the nodes either have 2 children or no children. In this type of binary tree, we can actually observe a property about the way that our size relates to our height. When we fill a tree starting at size 1, it takes us 2 nodes to populate the children of that root. And then it takes us 4 nodes to populate the children of those children. And then 8, and then 16, and then 32, and then 64. And you know what that looks like? That looks like 2 to the power of n, where n is the height of the tree. So we can say that to get to height n, we need 2 to the n nodes in an optimal complete binary tree. So if we take the opposite operation of the 2 to the n power, and we apply that, then we get log base 2 of n as the number of height for the given number of node. So how do we get closer to this with our existing binary search tree? Well, let's take this unoptimized size 3 tree as our example. We've got 3 nodes in our tree, and they go root, left, left. What if we consider the properties of our binary search tree? If we go with lefty larger, we know that the root is going to be smaller than its left child, which is in turn going to be smaller than its left child. And we know that the root's right child must be smaller than the root. But we also know that the parent of the left child must be smaller than the left child. So since we know that both the right of the root must be smaller, and also that the parent of the root must be smaller, we can actually swap the positions. We can swap the role of parent with the role of right. We can reroute our tree. That's called a rotation. We take this tree of size 3, and we change the root from being what used to be the root, which is this edge, to being the center node with 2 children. And now our tree has gone from maximally unoptimized to maximally optimized. And this rotation can be applied, well, just like everything, recursively to larger trees. That's the first trick in our book of how to improve the binary tree. These rotations can be performed in a number of ways for a number of reasons. My favorite example is a tree which rotates itself based on how frequently you access certain nodes, which means it will actually get faster every time you access something, so commonly accessed items will be accessed in better time complexity. Good luck, thank you for watching, and I hope you enjoyed. Height n. Oh, never mind, my mic was off. Hello everyone, hope you're doing great. Hope you enjoyed that little animation to start with. So today I'll be doing a tutorial on, I'll do an introductory one on the hash map and maybe the graph, and that's for the next assignment. I could also answer any questions you guys have about assignment 3, but seeing as it's the day it was due, it seems like it's a little bit late for A3 content. However, if you guys have any questions whatsoever, now is the time to ask, and now is a good time for me to explain to you what is going on with any A3 stuff that you might be wondering about, except for, of course, showing your code, because this is a recorded session. So if you guys have any questions, speak up now, else I'll get into the hash map stuff. I will take that as a no questions from you guys, which is devastating, but it's okay. I won't cry. Now we'll get into the hash map stuff now. So what is a hash map? Why do we care? Why do we hear so much about these damn hash maps everywhere? What is this stuff? Why am I showing you the solutions before I show you the question? All of these questions to be answered shortly. So what is the hash map? First, I'll send you guys the GitHub link for the project from today. And let me just get that really quick. The GitHub link is ici. Shout out to Mr. Croissant Friend, who made a great tester for this last assignment. I was just checking it out recently. That is great, but I'm going to show you guys tutorial 14 instead. So to the chat it goes. That is what we will be looking at today. We're writing this hash map. This hash map is an interesting data structure. First, I'll explain to you what a hash map is supposed to do. Well, a hash map is like a dictionary in Python. It creates an association between an object and a different kind of object. So you've got, let's say, a string and an integer, or a shape and a color, whatever. You can map any kind of thing to any other kind of thing. That's why it's called a map. What does a map let you do? It lets you look up the value given a key in O of 1. What do I mean by key and value? Well, the way a hash map works is it's like a fancy array where instead of using a number, an integer as an index, it uses an object as an index. How do you use an object as an index? We'll get into the nitty-gritty of that shortly because it's kind of cool. But for now, let's just think about it like this. It's sometimes called an associative array or a dictionary. And what these mean is that you have a relation between an object which isn't an integer as the index, and an object which is whatever you want as your value, as whatever's stored in the data structure. Now, when I said an object that isn't an integer, I mean it can be an integer. It just isn't like the primitive int that we use for an array. Before I get into the writing of the hash map, I'll actually show you a use of the hash map in a graph. But graphs are hard to explain. So maybe instead of showing you a use of a hash map in a graph, I'll show you a quick method which can be written using a hash map, and I'll even just use the Java util hash map. Hash map demo. And that will give you an idea of what our goal is. So in our hash map demo, I'm just going to create a public static void main string args as standard, and I'm going to say hash map, and it's going to be mapping strings to integers, and it's going to be age of celeb, right? And now that's going to be equal to a new hash map, and now we're going to say age of celeb dot put, and now let's just say what's a step? Justin Bieber, and I don't know how old he is, but I'm gonna guess he's 44, right? So age, we got a celebrity and we've got an age. Now, if we want to know how old a certain celebrity is, we can say, if our database contains our value, so if contains key Justin Bieber. So if there is a value associated with Justin Bieber, we can say system.out.println age of celeb .get Justin Bieber. Now we can already see how this is kind of useful, because we can get some kind of object given some other kind of object, and it's full of errors here because we haven't written any of these methods. I'm just going to return null for these. I don't know if we're going to get to the graph today, because, well, that's a whole other concept for me to explain, and I feel like I want to do some animations for that or something, because it's kind of complicated. But for now, return null, and hello, I'm just doing the hash map and the graph today, and if you have any assignment 3 questions, you are welcome to ask, and return 0, and return false. I'm just writing out these method declarations so that they, let it compile, and then I'm going to be able to show you a demonstration of how the hash maps work. Hash map demo, and the hash map or bad map class still is bad, so I'll just put 0, and I'm putting these fake return statements just so that it compiles, return false, and the rest of them are void except for these, which are return null, and return null, return 0, and return false, and return null, and return null. Sorry, I didn't do that before I sent out the thing. So now if we run that, or if we run hash map demo, we can see the function of a hash map. We've associated now the age 44 with the celebrity Justin Bieber. Now we can add more ages to this, so we can say age of celeb dot put, let's say Ariana Venti, and then Ariana Venti is obviously 28, sure, right? And we have all these various things. So we can print off these various ages. Now we can do the same thing, and we can say, if age of celeb dot contains Jack Human. Does it have that? Well, we'll print it out. Jack Human's age. Do we know it? Well, we never put it in there, so we can't find it. That's how it works. Same kind of thing as an array. If we used an array, we could say like maybe integer ages is equal to new integer, and then this is an array, so we'll do it like this, and then we'll say 44, comma 28. But now we kind of have to remember, right, that age 0 is going to be Justin Bieber, and age 1 is going to be Ariana Venti. So that doesn't work too well, right? Like, this is why the hash map is nice. Now, why else is the hash map nice? Well, it also lets us put any arbitrary object in here. So instead of age, we can actually put a list. So why don't I instead say hash map string, comma, list of string will be movies of actor, let's say. So we can say, and let's actually import list as well. Now we can say movies of actor equals new hash map, and we can say, let's say array list string movies of Jack Human is equal to new array list, and then we can say movies of Jack Human dot add, let's just say Les Miserables, and whatever else we want to add, like movies of Jack Human can have The Worst Showman, whatever. You probably know Jack Human's movies better than I do. Then we can say movies of actor dot put Jack Human and movies of Jack Human, right? So we can associate any kind of object with any other kind of object. And now we can system out print line movies of actor dot get Jack Human. And, well, we can see the list. So that's the function of a hash map. It maps keys to values. Now, a couple other quick things about the hash map. Values are unique. So if I put first this and then I put null, so movies of actor dot put Jack Human null, right? Then we'll run this. Now it's going to be null, right? Because it'll override whatever I put for the given key. Right? Okay, so since we know that these are, these are known, these are dual duplicate keys, those are overridden, those are the core functions of the hash map. But how does the hash map actually work? Well, before I get into the decent implementation of the hash map, I'm going to write a really crap implementation as well. So I'll call it public, or I'll just call it class awful hash map. And this one will be only for strings, right? Now this class awful hash map has a, let's make it a field. So private string, right? And it'll be, well, actually no, we can't have a string array. We'll have to have a public array of, or a private array of pairs of some kind, right? So we'll make our pair object a string, and it'll associate with, let's just say, a different string. And let's just create that object here. So class awful hash pair. So we'll have a string key and a string value. So now we'll have an array of these. So private awful hash pair buckets, and I'll tell you why it's called that in a second. And that'll be it. And then we'll have our constructor, so public awful hash pair, or awful hash map, hash amp, didn't even spell it correctly. What's wrong with this? Sure. Now we'll say buckets is equal to new awful hash pair, and then it'll have a size of, let's say, 10. We're not even going to implement resizing because it's so awful. And now we'll say public void put string key, string value, right? So now we'll create a constructor for this really quick. So generate a constructor, which takes both of these as inputs. And we'll say, as well, public, private int bad hash code is going to be another method. Now, this is how we actually get the index for where we're going to put it into our array. So we're going to say return, and it's also going to have to take a string, so string key. Now it's going to take key dot to char array 0 mod our awful hash pair dot length. Now what does it do? This makes our awful hash pair, no, it's called awful buckets dot length. So what this is going to do is it's going to return a number based on the key that is smaller or equal to the length of buckets. What does that mean? Well, we will have a we'll have a number here, right, based on the first character in our string, and that helps us narrow down which string it is. I'll go through with the debugger to explain it, but first I'll say buckets of bad hash code of key is going to equal to new awful hash pair of key comma value. Right? Now this is going to actually fill our hash map. Now public void get string key will return buckets at bad hash code of key. Now what does this code do? Well, and also what's wrong with this? It's not void, it's going to be public string get. And then this is going to be dot value. So this is going to get the value for a given key. This is the basis of how a hash map works. It's just this class here. We've got a pair, which just has 2 items. We have a method which compresses our item down to something like an integer. So this encodes our item as an integer. A way I show it here is that it takes the first letter of the string. Now, what can this be compared to in real life? Well, this can be compared to having people grouped by the first letter of their name, right? What's faster? Is it faster to iterate through all of the people in the class and ask them what their name is? So what's your name, what's your name, what's your name, what's your name? Or is it faster to put every single person in the class into a separate line based on the first letter of their name, and you know that the name you're looking for, let's say, is Alfred? Well, then you know that you're going to have to go to the people with A names because, well, Alfred is an A name. In fact, if I want to make this better, I can make this 26 size. And that should be roughly the amount of letters in the alphabet. And this won't always work, right? Because there's capital and there's lowercase. That's why we mod it. And because the ASCII value of a character is not going to be 0 for the first letter of the alphabet. Whatever. Well, we know that this will still correspond to people get placed in a certain index of this array based on their name, based on the value of that. So now if we try to do the exact same thing as up here, but instead with the awful hash map, so we can say awful hash map, and it's not generic, it's just there, is equal to age of celeb is equal to new awful hash map. Awful hash amp. Yeah, sure. And this one already exists, so we'll call it age of celeb 2. Right now, age of celeb 2.put, and we have to put a string here. Right now, integer ages is that whatever. Now we can ignore that. And now this all works, and we have to say age of celeb 2 though. Age of celeb 2, age of celeb 2. We'll wrap this with string.value of. Or we'll do quote 44, quote 28. Now we don't have a contains key anymore, so we'll just have to trust that these are there, and we'll get a null pointer exception if they're not. And then this one is just going to go away. And this age of celeb 2.get. So now if we run it, we should get the same output of 44, right? Because we've gotten Justin Bieber. Now if we add multiple things, we can add Ariana Vente as well, right? So let's also just system out print line, out.println, age of celeb 2.get Ariana Vente. And then let's also say system.out.println awful hash map dot what can we get? Well, let's make this just not private. That's terrible, but I'll just show it anyway. Dot, not alpha hash map, it's a to sub 2 dot buckets, and then we'll just do arrays.toString. Right. And then we'll have to create a toString method for hash pair. Let's just do that. Generate toString. Bam. Okay, so now we've got a bunch of nulls, and we can see that that there's 2 of these indices which have these hash pairs, right? So we've got awful hash pair Justin Bieber and awful hash pair Ariana Venti, right? And these are in different indices of this array. That's how a hash map works. It gets its index based on, well, here's the first character of the word. So here this index was whatever this was, like index 7 or whatever. This one got index some bigger number. And then it sets the value of the array at that index to be that which is your hash pair. And then that is how the map works. That's how it does lookup. It uses that same method. It's a one-way function, right? So you can always get the same hash number for a given object. A given object will always return the same hash number because, well, it's just a unique function. It works in one way on all of these different things. Yeah. So that's the essence of a hash map. This is our terrible hash map. And that's how it's implemented. Now we can actually do a better one. How do we do a better one? Well, there's actually a better way than using the first letter. There's a more generic way to get the hash value of a given function. And that way is actually to use something built into Java called hash code. And that's what's actually used in the real hash map in Java. It's the thing called hash code. And it does some math things that are complicated to explain. And it just returns a number based on the hash value, which is a fancy word for, well, some way to make an object be able to be encoded in less than the object takes up. Like, you don't have to encode all properties of an object, you just get a number from it. This is, of course, used to choose the index of where it goes in the array. But now our hash map wouldn't be too useful if it was of a fixed size. So we actually have to create a hash map of a changeable size. And to make a hash map of a changeable size, we probably want to have an array list, and we probably want to be able to change the various values in our hash map with relative ease. So, if we go into the actual hash map class, our bad map class, first we have to come up with what our fields are. Now, there's actually a lot of fields here, and they might not be immediately obvious as to why they exist, like what they do, but I'll be sure to explain them and make it very clear. So, the first thing that our hash map needs is it needs to have some sort of array to store our stuff, right? But there is a problem with having an array. An array can't be resized. So, and an array also can't contain generic objects. So what I have to do is I have to create an array list, and it's going to contain our bad pairs. Bad pair is the name I give to our hash pairs, and it's going to be k, v, key, value, and then it's going to be called buckets. Right, simple as that. But remember when I said here in our original code that a hash map's key is unique, but you could have actually a collision, because remember, we only take the first letter. That's only what we consider. So if I also put, as well as Justin Bieber, I put Jack Human in here, it might override Justin Bieber. Right? And Jack Human must be like 12, 14, sure. Right? So if I put Justin Bieber in here and Jack Human, Justin Bieber is going to be gone. Only Jack Human is there because they both have the same first letter of their name. That's what's called a collision. That's where when you have both Justin Bieber, who has a J name, and Jack Human, who has a J name, our hash code algorithm, it only considers the first letter. So if you have two people with the same first letter of their name, then you're going to have what's known as a collision, and that is going to cause a problem. All right, so how do we avoid this problem? Well, why not, instead of maintaining just one object reference in the array list here in the buckets, we can actually keep a list. We can keep a linked list of every item that corresponds to that hash value. So this will be the list of all the people with the same first name, for example. So instead of saying, okay, we're going to assume that everybody has the different first letter of their name, here we're saying, yeah, we can acknowledge that there's going to be people who have names that are different from each other's names, but have the same first letter. That's why we have a linked list in an array list of buckets. Hopefully that's clear to you. Now we have a private int number of buckets, which is going to be tied to the number of buckets in our thing, but I digress. We're going to use that a lot. Now we're going to have a private int size, and that's going to be 0 because that's what it starts as. And we're going to need a couple of constants. What constants do we need? We need a load factor and a default size, and I'll explain why we need both of these things shortly. So static final int default size, and I'll make this a fantastic number with no significance whatsoever. That's actually a bit big. Maybe I'll do 15, 10. Right? It doesn't really matter. We can put whatever we want. And now private static final double load factor is equal to 0.7. Why not? All right. Load factor and size are quite related. What is a load factor? Well, let's say that we have this list implementation, right? And we have, let's say, 100 people with A names, and our hashing algorithm only considers the first letter. Well, our runtime complexity is going to suck because it's going to have to iterate through 100 people to get to the one we're looking for. The load factor is how long these lists are compared to how big our buckets are. So we know that the list is going to be shorter if we have more potential. So if we consider the first 2 letters of the name, we're going to need more buckets because we're going to have more possible combinations. We're going to have like the possibility of AA, we're going to have the possibility of AB, whatever. So we're going to need more buckets, but our lists are going to be shorter in each bucket because there's going to be fewer people who have a name that's AA or AB, right? We're going to have fewer people who fit into each of those categories, but we're going to need more categories. Our load factor is the ratio of categories, so the ratio of groups to size of group. So if the size versus the number of buckets exceeds this number, we have to increase the number of buckets and change the hash algorithm to give values from 0 to the new number of buckets. So the first name's example holds there. Default size is just how many buckets there are by default. All right, so how do we do a constructor for this? How do we set all of these variables correctly? Well, first thing you have to do is we have to instantiate our array list. So we can say buckets is equal to new array list. But the thing about array list is that it doesn't actually start like an array. You know, an array is a pre-allocated block of memory with a certain size. So before I was able to just set our array with a certain size and have it work. If we do that here, even if we pass the default size as a parameter, it won't actually be filled with what we need because we need it to have empty linked lists inside, right? So we can say, well, first number of buckets is equal to default size. And then we can say for int I equals 0, I is less than number of buckets, I plus plus, we're going to fill our array list with linked lists. So we're going to say buckets.add new linked list. And it's going to be a linked list of, well, bad pair k comma v. Right, so we're filling our buckets with these linked lists, and that's going to make it so we don't get null pointer exceptions later. So our buckets are all full of these empty linked lists. So now we have our constructor done. We have an empty map which we can access stuff in. But how do we make our map actually work? Well, first, how do we know our size? Well, we just return our size. Easy peasy. How do we return is if it's empty, we return size is 0. Easy peasy as well. But how do we put something into our hash map? That can get a little bit more spicy. Well, the first thing we need to do is we need to figure out a way to get our hash value. So how do we turn our key into an index of an array? Well, there's actually a way to do this that's built into Java that will help us. And I think that in any assignment, I'm not sure, right, because I haven't seen the assignment, but I'm pretty sure that any assignment we're going to have in Comp 250 is going to let us use the Java hash function. So we're just going to give you one. So int hash value is equal to, and I'm going to take the absolute value because this hash function can give you a negative, ABS of key dot hash code, and that is how you get the hash value of an item. Now this hash code method depends on the actual implementation of the given object. So every object is going to have a different kind of hash code, and that's going to depend on the actual object that you are working with. And the example of a string was not how a string does it, but you could get a really crappy version of the hash code by just taking the first letter of the string, or summing all the letters of the string, or whatever. So now we're going to return the hash value mod the number of buckets. So this ensures that the output is less than the maximum index of our array, and this generates a unique number for each object we put it through. Now notice that this is also O of 1. So we can do these lookups in O of 1. So how do we use this to put something into an array? Well, first we have to figure out whether or not there's already a linked list in the given index. So how do we know this? Well, we say our int index is going to be equal to hash value of the key, right? Because that's what the index we're going to work with is. And now we're going to say we'll find our linked list. So our linked list of our bad pairs of k comma v list is going to be buckets.get at index. Right? So this is the list we're going to work with. What is it not like? Oh, I have an extra. No, that's fine. Hello? What's wrong? Oh, okay, I wrote that wrong. It's not going to be bad map. It's going to be bad pair. Okay, that's fine. And is this one bad map? Oh, it is. Okay, I meant to say bad pair over here. Bad pair. Right. So now our list of our bad pairs is here. And now we're going to have to see if it's going to replace something. So if the key is the same, we replace the thing with the same key. Note that multiple keys can have the same hash value, just as multiple names can start with A. So it's not a given that we have or don't have something to do with this key. So what do we have to do? Well, we have to iterate through our linked list, and we have to find if there's something to replace or not. So I'm going to create a boolean did replace equals false. Now I'm going to iterate through our list, and I'm going to see if we're going to replace something. So we're going to say for bad pair key value in our list. So pair in list. We're going to say if pair dot get key dot equals key pair dot set value, and we're not going to improve our size here, right? Because in this situation, our size doth not increment because we just replaced something that was already there. So we don't put size plus plus, but we do put did replace equals true. Right. Now here we can say if it did not replace anything, we can just say list.add new bad pair, and we're going to put our key comma value. Right. So this is our add method, and we're going to do size plus plus as well. So this way, if there's if there's something in there, then it's going to replace it. If there's not, it's going to not replace it. And it's really quite that simple. Except for the fact that we need to make our array bigger if it's not big enough. We can't just add to our list willy-nilly. We have to make sure that our list is not hashing wrong. Because remember, our hash is bounded by the size of our list. So our list cannot increase past the point of its size without us rebuilding our array list. So what we have to do here is we have to say if, and then we cast it to double because we're about to do some division, our size divided by our number of buckets is greater than our load factor, right? Because that's the definition of load factor. Our load factor is the maximum ratio of the size over number of buckets. If that exceeds the load factor, we have to rehash. What does rehash mean? It means it resizes the array, and it redoes the hash mapping for all of the stuff that was already in it. So we're going to have our array list. We're going to create a temp. It's just basically doing a copy. So we're going to do a list of linked lists of bad pairs of keys and values. And this is going to be old. It's going to be equal to buckets. Now we're going to say buckets is new array list. Just going to empty it out. Now we're going to say, so number of buckets is equal to 2 times, or yeah, just times equals 2. Right? Simple, easy peasy. Now we can say size is equal to 0 because we've emptied it out. And now we're going to say for equals 0, I is less than number of buckets, I plus plus. We're just going to fill our array list with new empty linked lists. So buckets.add new linked list, right? And this is not the best time complexity because I'm doing dual for loops, but oh well, sucks to be me. You can make this more efficient if you'd like. Linked list of bad pairs so for every item in our old values, k comma v, pair in old, add or put old.key or pair, I guess, pair.key. Huh? Excuse me? Oh yeah, pair. I have to do nested for loops. Oopsies. Pair dot for each. This add. Why does it not like that? Does it not want me to add? Okay, fine. I'll do a normal for each loop. I'll stop trying to flex. And I'm just going to do nested for loops to that pair. I should have named these better. So this is for everything in list. We'll have a bad pair k comma v pair. Now we'll just say add the or put the pair comma or pair dot get key pair dot get value. Right. So now we're just going to repopulate our hash map with what we used to contain. And what's wrong with pair in list? So now we just refill our data structure back with what we removed from it. And that's how we resize our data structure. So we've got put, we've got remove. Oh no, we got remove. We got rehash. Now we got to do remove. So remove just gets rid of something from the hash map. How do we do it? Well, we say first our index. So first int index at bucket is equal to hash value of key. And that's the index we're removing from. In fact, we can copy over the linked list thing. Right. Now we're just going to say get index at bucket. Right. Now we're going to say bad pair to remove equals null, and now we're going to iterate through our list to try to find it. So now for bad pair k comma v pair in our list, if pair dot get key dot equals our key, we're going to say to remove equals our pair. Simple as that. This is the way we identify our pair. So if to remove is not null, then we're going to return null. If to remove is not null, what we're going to do is we're going to say list remove to remove size minus minus return to remove dot get value. So this way we're able to remove the item we were going to remove from our list. If it's not null, we iterate through our list to find the object we're trying to remove. We check if it's found. If it is found, we remove it. If it's not found, well, we return its null. And if it is found, we return its value. So that's how we do remove. It's a really simple method. So what do? Well, we find the thing we ought to remove. If found, remove it. If not found, return null. Easy peasy. How do we get a value given the key? Well, also exceedingly simple. Except now, instead of returning, or instead of removing the one we're trying to remove, we just say return pair dot get value. So very similar. We just find the linked list of pairs that corresponds to our key. Then we simply iterate through our list till we find our pair, and then we return its value. It's a very fast lookup. It's just O of 1 sorta, except that it is actually bounded by the length of the list, which is bounded by the load factor. So there's a bit more complicated math that goes into the time complexity, but we can expect that it's going to be somewhere around O of 1. It's not going to take substantially longer than O of 1 if our load factor is correct. Now there's a couple more methods that are very useful that are actually not part of a basic hash map, but that are so useful I'm going to write them anyway, and they're also really easy. Contains key, very simple. We do a flag, so boolean contains equals false. Then you already know the procedure for this stuff. We for loop through our linked list, but now if it equals, instead of returning the get value, we just say contains equals true. True, right? Now we're just going to say return contains. Very easy. Now, why is this if statement yellow? Probably because, yeah, it could have a break. Nice. Okay, that's a very simple method. Also, just copy paste it. We already know our methods for traversing through a hash map. How do we get our keys? Well, that's also quite simple. Well, I'm using a set. A set is just a type of a data structure in Java which can only contain unique values. You can say set k output is equal to new hash set. It just shows hash set for no good reason. Now, for every list of pairs in this thing, so every linked list of bad pairs of keys and values called list in the buckets, I'm going to also iterate through for every bad pair for every bad pair k comma v pair in each list. Nested for loops suck. Set.add this output.add. Okay. Dot key. Right, now we just return output, and now suddenly we've got our hash set with our keys. Now, how do we return our values? In the exact same way, except instead of k's, we have v's. So v, and then return.getValue. Also really simple. See, it's one of these things where the methods are all really simple and similar to each other. And now we've got a fully working hash map. How do we know our hash map works? Well, if we run this test I wrote earlier, we can see that it indeed runs. Or does it? No, we have a missing return statement. Get forgets to return. Return null if nothing is found. Sure. Now if we run it, yeah, we can see that it's added 19 strings. There were 19 strings in there, and it's removed all the things successfully. But let's just do the same example we did before with the celebrities. So where is our main method? Let's just nuke all of that except for our bad map of string and integer. So we'll say map.put. In fact, since this map is so similar to the one we wrote over here, we can actually just do it again. So we can say this, and just instead of hash map age of celeb, we will do bad map instead. So where's our main method? Here it is. And then we'll say bad map, and then it's going to be string comma integer. Not string. This isn't assignment 1. String integer. It's going to be called age of celeb equals new bad map. Now we should observe that it behaves the exact same as our other bad map, where it'll go through and yeah, it'll say that the age of Justin Bieber is 44, and then what is null? Well, yeah, it's saying that Jack Human has null movies because it overrides the key. If we don't override it, we can actually see that the movies of Jack Human, and instead of using hash map, we should be using bad map. And it is just a drop-in replacement for hash map, as you can see. I've written it to be very, very similar. We can see that the list of movies for Jack Human is Les Pas Miserables and The Worst Showman, which is accurate, as everybody who knows movies knows. And that's like sort of the function of our hash map. Again, hash map's advantages. O of 1 lookup, O of 1 putting, maps any object to any other object. Imagine it as an array, where instead of being an int, the index is any object. Does anybody have any questions regarding hash map or assignment 3 or whatever? You're welcome to speak up or say in the chat. Yeah, go ahead, though it's a recorded session, so avoid specific questions about your code, but anything general is okay. Okay, so in IntelliJ, what you have to do is you have to go VCS, then get from version control, like it says in the docs, and you have to paste in the link. So what is the link of it? I don't have it, but you can find the link. You have it because you obviously tried, right? And then you'll get it, and yeah, you paste the GitHub link into there. You don't just download it from GitHub directly, right? You paste your link like that into IntelliJ. Then your project will download. It'll create this environment, and it's using something called Gradle to manage your libraries. With Gradle, it'll download all the libraries for you, but you have to run it through Gradle. I don't have an example project here. I do have it downloaded, but I have it downloaded with my solution code, so I can't really show it directly because I might just dox myself and give out the solutions. So I can tell you in theory how a Gradle project will work. You can run it. Then over here there will be one called Gradle. Like one of these tabs will say Gradle, and then in that tab which says Gradle, you will be able to run it from Gradle, and that will help you out. And then that will download everything for you. Well, yes, I believe that tester was never made to work with Eclipse. I think it might work with Eclipse, but I've never tried it, and I saw where it was posted that the guy who posted it said that he is not maintaining it for Eclipse. So I guess nobody's ever tried, is the situation for Eclipse. You can try it. Gradle works in Eclipse too. I think it will take some additional setup, and nobody's tested it yet. So good luck. If you want it to be the easy process, and you can always ask the author. I think he'd be happy to help you out as well in the setup. You can ask him how he recommends that you do it. You're able to go into it with IntelliJ. You simply clone like that. Everything should work by default. All you have to do is take your file, so your dog shelter.java, and drag it into here. You literally just drag the .java into this source folder, and then it's all ready to go, and all of the tests will run. Yeah, for sure. Good luck on your assignment. Yeah, and if there's any further questions, you all are welcome to ask. And I will do a quick lightning review once again of the hash maps. So what is the purpose of hash maps? Hash maps map objects to other objects. How do they work? Well, a hash map will have an array or an array list which contains buckets. Buckets are just chains of objects that have the same hash code. And then it uses the hash code as the index. My best analogy for hash code is imagine that you take the first letter of somebody's name. A hash map lets you look people up faster because if you just take the first letter of people's name and put them in a room based on the first letter, you're able to know exactly what room you have to go to. Let's say that you are in McGill, right? And you're going to the office of a professor for office hours back before the Rona. What would happen is you would go to, let's say, Professor Julia's office. Well, you know that her door is the one that says her name on it, right? And you know that it's going to be, let's say, room number like 642. I don't know what room number it is, but let's say 642. So you know that you can look up the professor by going to room 642. You don't have to, iterate through every single room at McGill to find the professor. You've mapped in your head that Professor Julia is in room 642. So if I want to go to office hours, I go to room 642, right? That's the same idea with a hash map. You can map an object. So here we're mapping a person object to a room. Or I guess you're mapping the room object to the person, however you want to perceive it. But you create this association, and then that will let you access it in O of 1. Again, instead of iterating through every room at McGill, or maybe log of every room at McGill if you find some fancy algorithm to do it. You know exactly where you're going and you go there. That's the hash map. That's its advantage. It's also memory it's not terrible. It's not super wonderful because you have empty buckets, but there shouldn't be too many of them in a great hash map. And then, that hash code can map things, and the way it maps them isn't by taking the object. The way you shove this object into an array is you do what's called a hash code, which is this complicated mathy algorithm. But my best analogy for a really crappy version of the hash code is to just take the first letter. So if you were to map people based on their names, again, you take the first letter of their name. You know that people whose name starts with A are going to be in the room A. So the room A is going to have all the people whose name starts with A. That's going to speed up your finding of people. That is the whole function of a hash map. Now, I only have 9 minutes left, so I can't do the graph implementation for you, but I can explain what a graph is, what it does. It's going to be really relevant for upcoming stuff. You might have seen it in the lectures before, and I'm going to explain to you how hash maps and graphs have so much to do with each other. So, you know that a graph is a collection of vertices which may or may not be connected to each other via edges, right? Let's say that a graph could be a map of airports. You have, LAX and whatever other airports. You have all these airports around, YUL, YVR, all of these airports, and they are linked to each other, but maybe not directly. They all have links to each other, right? How do we store, how do we get the links of a given vertex? How do we get the airports connected to a given airport? Quickly, given the airport. So I say, I know that the airport here in Montreal is YUL, like it's Airport Pierre Elliott Trudeau. I know that the airport object I'm looking for is Pierre Elliott Trudeau. But I've got this list of 10,000 other airports, which all have their own map between a list of other airports they're connected to and the airport. That's the hash map, right? It's a map of airports to airports that are connected to it. So if I have an array list, for example, of these lists of airports, I have to go for every pair of airport list of airports, or I guess for every airport in this list, I have to see if it's the right one and then look at its list, right? And that could take me up to 10,000 iterations because I have to look it up. And let's say I want to go with 2 flights. I want to go from Montreal to LA and from LA to, I don't know, Japan or something. So if I want to go Montreal to LA, LA to Tokyo, then I have to do an array list iteration to find the connection between Montreal and LA, and then I have to do the exact same operation another time where to go from LA to Tokyo. You can see how that's really going to slow me down in this graph. I need some way, given an airport, to get all of the airports it's connected to in O of 1, and that is what a hash map is for. Given a hash map, I can put Montreal Airport and then the list of airports it's connected to as the things in the hash map, right? As the, well, I guess that's from the vertex and the list of vertices it's connected to, so the edges. And then here, with this map, I'm able to say, okay, map, I am at Montreal. And the map will be able to tell me, Montreal, awesome. Well, we know that Montreal is connected to, here's the list. Right, and then I'll go through the list and I can get what it's connected to from that. That's why a hash map and a graph are so helpful to each other. The graph is built on the hash map. So to build a good graph, you have to build a good hash map. There's ways to do a graph without a hash map, but nah. Now the hash map method is fast, and the hash map method is what we like. What's an example of how a graph works? Well, here I've made an integer graph, which graphs various integers to each other, and here we've got like where graphs indirectly loop back to each other where they don't. That's all complicated. We'll get into it next week probably, and maybe I'll do a session on hash maps and a session on graphs. But for now, that's the core idea of the graph, and that's how the hash map and the graph are so related. And this hash map class, this bad map, is all ready. It's all done from today's session, and it's ready to be used for creating this graph. And then next time, I'm going to be able to build out this graph using this hash map we made, and it's going to be legendary. And those are the basis for our final project. They're going to be on this content. They're not going to be exactly like this, but same basis, right? And that should help you out. So yeah, hash map, graph, we'll do them. And then graphs have a bunch of other stuff. There's stuff like Dijkstra's algorithm to find the shortest path. And there's a whole realm of computer science all about graphs that we can get into, but we don't need to today. So, if there's any questions about anything, now is the time to ask. All right, so I'll give us one final recap, and if there's no further questions, I will finish up with the session. So, final recap. Hash map is basically an array that instead of using an int as an index, uses whatever you want as an index. How does it do it? It uses a hash function. An object will be turned into an integer. That integer will be used as the index. That is where in the array its corresponding thing will be put. You put hash pairs. Very nice. It allows O of 1 lookup, helpful for graphs. Bam. All right. If there's no more questions, I'll end the session now, and hopefully you guys all had a fantastic and informative time. Good luck on assignment 3. Y'all got this. I believe in you. I'll give you guys a minute or so for your questions, and that will be that. Oh, and the solutions code is already posted. It's on pre-solved on the branch on GitHub. So if you're wondering, my hash map and my graph solution, or just don't look at the graph part if you don't want spoilers, but the hash map solution is there. And you know what, maybe I'll make a new branch here and I'll call it like, just the, or Thursday solutions, just the math, right? And I'll push those for you, and see you guys all later. Have a great day. Good luck on assignment 3.